which is nothing but the meter bridge. Now, if I am going to revise you first, what is Wheatstone? Can you able to remind that which we have discussed in the last session what Wheatstone is? Actually, Wheatstone is the bridge of those 4 resistors when they are connected in the bridge. Okay, let me show you here. Suppose these are my 4 resistors. Say this is my key K2. This is again my resistor. Say P, Q, R and S. Okay, and this has been connected with the battery and again a key. Say this is K1. Now what happens is, whenever we are having the bridge of resistors in this form, and we know that whenever the current, when we press this key K1 and current start flowing through this circuit, and then we open this, when we close this key K2, then our balanced condition, that means when the galvanometer shows no deflection, this would be the ideal, or you can say this would be the balanced condition of Wheatstone. In that case, Ig would become equals to 0, and we have solved further that if the condition is balanced for Wheatstone bridge, then we have P by Q equals to R by S. This is the balanced condition of the Wheatstone bridge. And in today's session, we are going to discuss about meter bridge, which is nothing but the application of Wheatstone bridge. So let me start with that. And before that, I have already discussed here what Wheatstone is. We are going to solve again this, because this is the application of Wheatstone. Sorry. Now, the word, the heading which you are able to see here is meter bridge. Again, it is comprised of 2 words. One is meter and one is bridge. This is also called slide wire bridge. Here is again one word slide wire and the second word is bridge. So, these 2 meaning has their particular meanings here. If I am talking about meter, then that means it is having a meter length, this AC, a wire of 1 meter which is being connected and stretched between these 2 points. And why the bridge? If I am saying this is the application of Wheatstone bridge, that means again we are going to find the 4 resistors in the manner in which the Wheatstone bridge has been followed. Okay, so it's now the time to start with what is meter bridge, what is its working, and why are we using this. So my dear friends, first of all, I am going to discuss before you the structure of meter bridge. Just look at this side. Here is the wire AC, and property of this wire is again that this wire is made of alloy, which is manganese and constantan. Okay, so if I am talking about the meter bridge, the wire, that means this pink colored wire which I have drawn for you, this is in actual this is not pink color, but because I am having pink chalk, so I think I should have shown you this wire in a very colored manner. That is why I have just drawn it in a very beautiful color, that is pink color. So this is the wire AC and it is of 1 meter. That is why I am calling it a meter bridge. Here it is a meter scale connected with this. There are 2 resistors R and S at 2 ends. These are the 2 copper strips. They are at right angle. This position, this is what? This position is what? This is at right angle. And similarly, these copper strips are being connected here. So these are connected in right angle position, and across these gaps, my 2 resistors are being connected. what to do with these two resistors? Why I am applying these two resistors? In actual, I have to find the value of one unknown resistance. This is the application of meter bridge. That means we can find the value of an unknown resistance where we have already know the value of any specific resistance. Like in this case, if I know the value of R, I can find the value of S. Alright. So here I have connected two resistors. One is that for which I know the value, and one is that whose value I have to recognize. Here it is a galvanometer which is again connected with the midpoint of this copper strip. Alright. Now one end of the galvanometer is connected across the midpoint of this copper strip, and the another end of this galvanometer is connected across this wire in the mid of this wire at point D. Alright. If now I say, and also it is being connected with a battery and a key. When the key will be getting closed, current I would be started flowing through this. And now when the current flows, what happens is, since again I am repeating myself, this is the application of Wheatstone bridge, so nothing will happen but the condition of Wheatstone will be getting followed. Okay, so here I am saying that my S is what? My S is standard known resistance. And I have to find the value of R here, resistance, from a resistance box. Now what is resistance box? We are going to discuss about this resistance box in detail after this session has been complete. But before that, I think the focus should be on the meter bridge. Here now, I know that value of S is something standard known resistance, and I have to find the value of R. Now in this portion, if you are going to see that if I am going, since this is my wire AC and this is my galvanometer connected with it, I am going to change the value of resistances from here. Any resistance value I can take, I am talking about S. I can take any value of S. Then what will happen when the current I would be flowing through it? Can I say that my length of portion AD will be equal to L1. Say this is the midpoint, which is the balanced condition of meter bridge. If I am saying this as AD, then what would be the length of this DC? Because I have said earlier, this is 1 meter length. 1 meter equals to 100 centimeter. So if I am saying in the terms of centimeter, then this is 100 centimeter wire and this length is L1. So that would be quite obvious. This is 100 minus L1. Alright. So if I am saying length of portion AD equals to L1. So the length of portion DC would become what? (100 minus L1). Alright. So now just watch at that this is the balanced condition. What if the condition is not balanced? Then what will happen? We are particularly talking about the balanced condition. That means whenever the galvanometer shows no deflection, that means no current, wherever the point should be, whether the point D should be here or here or here, whenever on touching this galvanometer at this point, at any point of this wire, and galvanometer shows no deflection, that means no current. So that means that would be following the condition of Wheatstone. That means the current in the arm, in the middle arm where G was connected, that means Ig would be equals to 0. And we know that when Ig equals to 0, then what is the condition? P by Q equals to R by S. Now you will be saying that, ma'am, in Wheatstone bridge, we were having 4 resistors. But what in here, in this case? I will tell you, here you can say there are 2 resistors. But my dear friend, this wire which is being stretched over these 2 points, that is AC, this is also having some resistance. And if I am saying I have divided these into these 2 length of portions, that means if I have found the balanced point in this wire, then I have said that my balanced length of this portion is L1 and this portion is 100 minus L1. Now can I say the resistance of portion AD is what? Suppose if a wire is having length L, so that, and say suppose the resistance is R, okay. Say in this case, resistance per unit length, if I am giving you this condition equals to Rm, okay. So this is resistance per unit length. So can you now tell me what would be the resistance of the complete length? This is very easy. If you are knowing that resistance per unit length or per centimeter, or you can say per centimeter is Rm. So what would be the resistance of the wire having length L? That would be Rm into L. If now I am talking about portion DC, if I now talk about portion DC, then the case would be resistance of portion DC will be equals to Rm into 100 minus L. We know that the length of portion DC is what? 100 minus L, and per centimeter, resistance per centimeter is Rm. So the length, complete length would be having resistance of Rm into 100 minus L. So now, since this portion DC and this portion AD is having some resistance, that means they are becoming resistors. So can I now see in this diagram that this portion AD is having resistance RML, this portion is having RML, and this portion DC would be having Rm into 100 minus L. Can now you see this, there are 4 resistance, this R, this AD, this S and this DC. So again there are 4 resistors, and in the mid of them a galvanometer is being connected. So now it has become a Wheatstone bridge. Simply now we are going to apply the balanced condition of Wheatstone bridge. Since we have said that current in the galvanometer, whenever the balanced condition would be achieved, then the galvanometer will show no deflection. That means no current. What was the function of galvanometer? It is just detecting the current in the circuit, and if it is giving no deflection, then that means there is no current in the circuit. That means Ig is becoming equals to 0. If Ig equals to 0, the condition of Wheatstone is followed. So now can I say that P by Q equals to R by S? That means if I am going to write it as my R upon AD will be equals to S upon DC. You can write here, since the condition of Wheatstone is followed, Wheatstone bridge is followed. So I can write it as R upon AD equals to S upon DC. And what is AD here? R upon AD is what? Rm into L equals to S upon DC is what? DC is Rm into 100 minus L. And in the very beginning, we have defined that S is a standard resistance. We have known the value of S. So we have to find the value of this R. So if I am going to find this value of R, can I write it in the form of R equals to S into RML upon Rm into 100 minus L. Okay. This Rm and Rm, that means the resistance per centimeter is getting cancelled with each other. So I would be left with R equals to S into L upon 100 minus L. Okay. So this is the value of that unknown resistance, and this is the value that we have known. Already we have known that S is something having resistance. L we have known by the balanced condition, and 100 minus L would be, obviously we would be knowing. So this value, that means the value of any unknown resistance, can be found using a meter bridge by this formula. The value, the S we have earlier defined, L we have known by just putting the galvanometer onto the wire, onto the meter bridge. Wherever we have found that my deflection is 0, I am having no deflection in the galvanometer, then I would be saying that this is my balanced point. And if I am going to measure this point from this end, then that would be my balanced length. That would be L1. And the remaining length would be what? Total minus this length. Total was what? Total was 100. And if I am getting subtracted this length, balanced length from 100, that would be 100 minus L1. So we are having this R equals to S upon 100 minus L. We have found the value of any unknown resistance, which was the application of meter bridge. So I think you guys would have understand now what is a meter bridge, what is the application of meter bridge, and what is the principle of meter bridge. Can I now ask you a question? Can you tell me the principle of meter bridge? You would be saying yes, ma'am, it is based on the principle of Wheatstone. Then you could have defined me a Wheatstone bridge. So if you will be asked about the principle of meter bridge, then don't worry my dear friend, you have to just tell them about Wheatstone bridge. Firstly, you will be telling that ma'am, Wheatstone bridge, meter bridge is based on nothing but the Wheatstone bridge. And then you will be defining what is Wheatstone bridge. Just look at this side, I have written here slide wire bridge. This is being written here. This is the another name of meter bridge. So what do we mean by slide wire bridge? Bridge, we know that why this term bridge is being used, because there is a bridge of 4 resistors. And why slide wire? Because here is a wire on which we are sliding the galvanometer, the point of galvanometer, and we are finding the balanced point. So the question number 1 says that 2 electric bulbs marked as 25 watt 220 volt and 100 watt 220 volt. These are the 2 specifications of 2 bulbs that has been given over here. They are connected in series to a 440 volt supply. So which of the bulbs will fuse? Whether any of the bulb is going to be fused or not. So we have been given the 4 options, whether both of the bulb will get fused only 100 watt bulb, only 25 watt bulb, or none of these. So what we have to check it out here, you can see over here 220 volt and 220 volt, both are being supplied with the same voltage. So we know that we are having one formula before us, that is P equals to V square divided by R, where P is your power, V is the voltage, and R is your resistance. In the given two bulbs, what we have with us is, first power is 25 watt and P2 is 100 watt. Now my dear students, what we can observe, since voltage in the given question is same, that is 220 volt. So from here directly I can say that P is inversely proportional to R, isn't it? So now here you can say that P2 is having more power. Since it is having more power, then that means it will be having lower resistance. So that means resistance of this P1, that means 25 watt bulb, is higher because its power is low. So that means its resistance is definitely going to be higher. Now because the resistance is higher, that means what? That means in this case, in this circuit where the two bulbs are connected, which is having same voltage supply, one is having higher resistance, one is having lower resistance. Since their voltage is same, so current, and one important thing, they are connected in series. So if they are connected in series, let me just show you by drawing like this. Say these are two bulbs. When they both are connected in series, what will happen? The current in both the bulbs will remain same. Now if current is same, one resistance is higher, second is lower, so definitely the one with higher resistance is going to be heated more. So the one which is getting heated more, that is going to be fused at that time. So that means the resistance, or you can say the bulb which is having power 25 watt, it is going to be fused. So the option that we are having with us here, we can see that 25 watt bulb. So that means this bulb is going to be fused, alright. So this question is completed, as I have already told you in the theory, that if you have learned the theory in the very easy manner, or you understood all the concepts, this is not going to be tougher for you. We will be now moving towards the next question, and the question number 2 says that in the given circuit that has been shown below, the key is closed at t equals to 0. The current through the battery is what? In the given circuit, we have been given one voltage supply, one key, one inductance, one resistor, that is R1, another resistor having value R2. Now here what are they saying? At t equals to 0. As you know that if we are talking about the inductor, if I talk about the inductor at t equals to 0, this is the property of inductor, that at t equals to 0, inductor behaves as an infinite resistance. Now since it is behaving as infinite resistance, that means no current is going to be flown through this inductance. Now in this circuit, if no current will be flowing towards this, suppose this is now has been removed, the yellow portion, this has now been removed. Now you are left with one voltage supply, one key, and the resistance R2. So now the current in the remaining circuit will be, let me just current in the circuit at t equals to 0 I equals to V upon R2. That will be the current in the circuit. So, in the given option what we have seen, V upon R2 at t equals to 0, V upon R1 R2 under root R1 square plus R2 square at t equals to 0. First of all, we have to check out the current at t equals to 0. So, from these four options, V upon RT at t equals to 0, I can see there are two options that has been available for us. So, that means definitely option number D and option number A can be reduced from here. Now, we have to check the current at t equals to infinity. So, as we have seen that at t equals to 0, the inductor behaves as an infinite resistance. We will now check at t equals to infinity, how does the inductor behaves? At t equals to infinity, inductor behaves as a conducting wire. It behaves as a conducting wire. As you know that if something is behaving as a conducting wire, that means the current is going to be flown through this wire. Now, I am going to remove this yellow portion from here. That means you are now having with you as this complete circuit. That means this L is now behaving just as an wire, nothing else. So, now I am going to remove this L. This is just behaving as a conducting wire. So, you are left with R1 and R2. Now, if I am going to find out the current in this circuit, I will be taking the R equivalent of the circuit. That means the combination of these two resistors. Here you can see these R1 and R2, they are connected in parallel. So, R equivalent at that condition will be R1 R2 upon R1 plus R2. This will be your R equivalent at t equals to infinity. Now, in this case, what is the current? Now, the current will be I equals to V upon R equivalent. So, you can directly put this value R equivalent. So, we will be having R1 R2 R1 plus R2. This is the value of current I at t equals to infinity. So, now we have to check it out from the options available that whether I is coming out to be equals to this or not. V into R1 plus R2 upon R1 R2, and the second one is V R1 R2 upon under root R1 square plus under root R2 square. That means this option is going to be deducted. The correct answer for the question is this. Alright. So, that was the easy question. As I already told you, if you are cleared with this concept, so no question is going to be tougher for you. We will be now moving towards the next question of the session, and the question says that, let me just remove it first and then I will be reading it for you. Okay. So, the question number 3 says that two conductors have the same resistance at 0 degrees Celsius, but their temperature coefficient of resistance are alpha 1 and alpha 2. The respective temperature coefficients of their series and parallel combination would be what? So, what we have to do? We have to find the series and parallel combination of their temperature coefficients, right? How we are going to proceed with this question is a very simple thing. We know that the combination of the two resistors when they are connected in series is what? If I am writing it as, that will be Rs equals to R1 plus R2, and if I talk about the parallel combination, that will be Rp equals to R1 R2 upon R1 plus R2. Now as they are saying that they are having the same temperature coefficient at 0 degrees Celsius, or you can say they are having the same resistance at 0 degrees Celsius. So let me just write at 0 degrees Celsius their resistances are R0 and R0, right? One formula that we know about the temperature coefficient is that R equals to R0 1 plus alpha into T. Right students? If you know this formula, you can easily apply this formula to solve this particular question. So how we are going to apply this here? We know that we are going to find out the parallel and series combination of their temperature coefficients. So how we are going to proceed? We are going to apply this formula and these combinations into this. So first of all, for series combination, if I will be talking about the series combination, we know that Rs equals to R1 plus R2, right? So let me just write here Rs equals to R1 plus R2. If I will be putting the value of R1 plus R2, that will be, let me just put this as Rs naught 1 plus alpha s into theta. Now I am taking one particular temperature theta. Let me just write at temperature theta, right? So at particular temperature theta, I will be having Rs naught 1 plus alpha s into theta equals to R1 plus R naught 1 plus alpha 2 into theta, right? Now from here what we can do is, we know that if we are talking about the series combination, so if we will be talking about the initial resistances, in that case Rs naught will be equals to R naught plus R naught, that is equals to 2R naught. So we are going to put this value into this particular equation. So put 2R naught in place of this Rs naught. So we will be having 2R naught 1 plus alpha s into theta equals to R naught. If I will be taking R naught from here as my common term, so let me just first of all open the bracket, R naught plus R naught into alpha 1 theta plus R naught plus R naught into alpha 2 theta. If now I will be taking R naught as common, so I will be left with R naught plus R naught, that is 2R naught plus R naught into theta, and I am left with alpha 1 plus alpha 2, right? 2R naught, if I will be bringing this R naught here, I will be left with minus, or you can say divide. If I will be taking it into division, that will going to be cancelled out there. So 2R naught is going to be cancelled out from here, and then we will be left with, let me just, what we have to do is just focus over here. We have put the value of Rs naught, that is 2R naught, we have been putting this value here. 1 plus alpha s theta equals to R naught plus R naught alpha 1 theta plus R naught alpha 2 theta, right? From here what I have did is 2R naught 1 plus alpha s theta equals to R naught plus R naught, that has been came out to be 2R naught. Now in these two equations, in these two particular terms, I have taken R naught and theta as common, so I am left with alpha 1 plus alpha 2. So if I am going to now divide this, I will be left with, let me just remove this equation from here, I will be left with 1 plus alpha s theta equals to 1 plus theta into alpha 1 plus alpha 2 upon 2, right? Now if I will be moving in the same direction, I will be left with alpha s theta equals to alpha 1 plus alpha 2 divided by 2. I am not going to solve this particular complete derivation over here. If you are going to apply the same approach, you will be left with alpha s equals to alpha 1 plus alpha 2 upon 2, right? Now in the options given to us, I am going to check for the series combination. So for series combination, I am having alpha 1 plus alpha 2 upon 2. Let me just remove this theta from here because we are now having only this much. So alpha 1 plus alpha 2 upon 2, I can see this is present in option A. This is not present in option B because series combination has been given as alpha 1 plus alpha 2. So this cannot be the answer. Alpha 1 plus alpha 2, again this cannot be the answer, but we are having a dilemma between A and D. Now what we have to do is we have to check for the parallel combination. Here we have done only for the series combination. To find it out for the parallel combination, we are going to apply the same approach. Again, for parallel combination, we are now having with us Rp equals to R1 R2 upon R1 plus R2. So your Rp into, you can write it as P naught equals to R naught 1 plus alpha 1 theta into R naught 1 plus alpha 2 theta divided by, you know what I am writing over here, R1 is R naught 1 plus alpha 1 theta, R2 is R naught 1 plus alpha 2 theta. Again same terms but in addition plus R naught 1 plus alpha 2 into theta. This is nothing but the 2. Now again if you are going to solve for this, you can see over here we can, if we are taking the parallel combination, we will be having R naught into R naught upon R naught into R naught. If we are talking about the initial resistances, we will be having with us R naught into R naught, that means R1 R2 upon, upon R1 plus R2. The same formula we are using but for the initial resistances. So we are now having, this is R naught square divided by 2 R naught. So R naught cancel, we are left with R naught by 2. So we are going to put this Rp naught as R naught by 2 in place of this. So just put this value, R naught by 2 into alpha p plus theta will be equals to R naught 1 plus alpha 1 theta into R naught 1 plus alpha 2 theta, or you can do one thing, you can take this R naught as R naught square in the beginning and you can take R naught and R naught as common from here. You will be left with 2 R naught into 1 plus alpha 1 theta plus R naught into alpha 2 theta. You can just move up to this step. What we have did is we have just put this value R naught by 2 till here and we have started solving. R naught into R naught, that will be R naught square. So I have taken it in the beginning 1 plus alpha 1 theta into 1 plus alpha 2 theta. If you are now going to open this bracket, you will be having R naught plus R naught alpha 1 theta. So here plus again R naught plus R naught alpha 2 theta. Now what we have did is, again I am going to just do it for you. R0 into R0, R0 plus R0, that is 2 R0, plus R0 alpha 1 theta plus R0 alpha 2 theta. That we will be having, right? Now from here, if I'll be taking R0 as common, so I'll be left with, I will be left with R0 by 2 alpha p plus theta equals to R0 square 1 plus alpha 1 theta multiply 1 plus alpha 2 theta divided by, if in this equation we are going to take R0 as common, so we will be having R0 2 plus alpha 1 theta plus alpha 2 theta. Okay. So now R0 and R0 has been cancelled from here. One R0 and R0. This has been cancelled. So we are now having alpha p plus theta equals to 2 into 1 plus alpha 1 theta into 1 plus alpha 2 theta divided by 2 plus alpha 1 theta plus alpha 2 theta. This is really a cumbersome method because this is the only method that we are having with us to solve the equation, because this is one simple formula that we are applying and just basic mathematics. You are going to have to apply the equations, have to solve this equation with the similar manner. Now you are left with alpha p plus theta. In the similar manner, if you will be reaching up to this alpha p, you will be again left with alpha p equals to alpha 1 plus alpha 2 divided by 2. That means you need to just resolve this equation. This we have reached up to here, but again if you are going to just fuse the equation, merge the equation, and at the last I can give you a hint. What you have to do is you have to just rationalize the equation. At the very moment when you are going to rationalize the equation, you are going to have this particular value. And one more thing, one more hint that I can give you in this equation is that this alpha 1 and alpha 2, these are very small values. So whenever you will be encountered with alpha 1, alpha 2, you can directly ignore them. Or if you will be having alpha 1 plus alpha 2 whole square, you can directly ignore them, right? So this was the hint for the further steps, because I am time congested, so I cannot tell you the whole steps. I am just time bound. Now alpha p is alpha 1 plus alpha 2 divided by 2. So yeah, I can see that in the option number D, we are having this option before us. So that means definitely this should be the answer of the question. In the circuit shown in figure, potential difference between points A and B is 16 volt. This is point A, this is point B. So the potential between them is 16 volt. Let me just write it, VAB equals to 16 volt, right? Now the current passing through 2 ohm resistance will be what? They are demanding from us that, they are just wanting to know from us that what will be the current in this 2 ohm resistor, in this resistor, right? Now what we have to do is, we have to first of all just take the current in this circuit. We will be considering, because you can see that, let me just draw it again for you. This is 4 ohm resistor. This is a battery with potential on this side, with the bigger on this side. Then again a resistor, and then smaller arm of the battery. Then again a 4 ohm resistor, and then point B. This is point A. This is 4 ohm resistor. This is a 9 volt battery. This is a 1 ohm resistor. This is a 3 volt battery. again it is a 4 ohm resistor, and in this one resistor is being connected, that is a 2 ohm resistor. Now what we have to do is we have to find out the current in this arm. That means in the resistor 2 ohm. So first of all, to knowing the current, we should be just supposing the current in the circuit. Now just focus over the question over here. As you can see that current always flows from higher potential to lower potential. So from here the current will be like this, and from here the current will be like this. Now let me just suppose that current I1 is flowing from here. Say this is I1 that is flowing from here. Now if I am going to suppose I am connecting a battery over here, so that means it is a complete circuit. From here B, the current will be flowing like this here. Alright. Now because it is a one complete circuit, so that means if I1 is coming from here, definitely I1 is going here. So that means it is again I1, right? Now if it is I1, let me just suppose that from this battery current I2 is flowing. This is I2, right? Now you can see this current is coming from here, this from here. So in this particular arm that is having 2 ohm resistance, the current that will be going in this arm will be I1 plus I2, right? Now again after going from here, this current will be I2, because I2 is going from here, I1 plus I2 is going from here, I2 will go here and I1 will go there. Like this we have divided the current in the circuit. Now we have to find out the current in this arm. So what we will do, we will apply first of all the Kirchhoff's law, Kirchhoff's voltage law. As I have told you, the two laws of Kirchhoff, that is Kirchhoff's current law and the voltage law, that means the loop law, loop rule. So here let me just using that Kirchhoff's law, and I am just applying this Kirchhoff's law in this particular arm, that is starting from point A and then going from like this like this. I am supposing the current in this particular arm. So now here the equation will become as 4 into I1 plus 2 into I1 plus I2, then minus 3. As I have told you in the lectures also, that why minus 3? Because in this arm, in this battery, the current is flowing from minus to plus. So that means we are going to consider the minus sign over here. Minus 3 plus 4I1. This is equals to, what has been given? VAB equals to 16 volt. So that means this will be equals to 16. This we have considered the equation 1 for this particular arm. Now we have to apply KVL, that means Kirchhoff's voltage law, in this particular loop. So let me just consider what I have told you in the KVL. We have to consider the direction of current, and if I am supposing the direction of current like this, so here what will be the equation become? The equation will be 9 minus 2 into I1 plus I2 minus I2. So the equation will be written as 9 minus 2 into I1 plus I2 minus I2. That means 1 into I2, because I am just considering I am applying the KVL in this particular loop. So then 1 into I2, that means minus I2, this will be equals to 0, right? Now from here what I can just consider this as equation number 1 and this as my equation number 2. So then what will happen? What I can do from here is I can find out the value of 2I1 and I2 from here. So that will be 9 minus I2 equals to 2 I1 plus I2. Right? I have found out the value of 2 I1 plus I2 from this equation. So that means 2 I1 plus I2 has been equals to 9 minus I2. Let me just consider this as equation number 3. Now putting equation number 3 into 1, we will be having with us 4 I1. In place of plus 2 I1 plus I2, we are going to write 9 minus I2 plus 9 minus I2 minus 3 plus 4 I1 is equals to 16. Right, students? Now what we are going to do is, I am just going to rub this equation now, equation number 1. So what we are left with now? 4 I1 plus 4 I1, 8 I1 plus 9 minus 3 plus 6 minus I2 equals to 16. So from here we will be having with us 8 I1 minus I2 equals to 10, right? 9 minus 3, 6. So we are having with us 8 minus I2, 8 I1 minus I2 equals to 10. Let me just suppose this as equation number 4. Now we can see that in equation number 3 and in equation number 4, if I am going to solve for them, I'll be able to find out the value of I1 and I2. When you are going to solve these two equations, you will see that your I1 will came out to be 1.5 ampere, and by putting this 1.5 ampere into this equation, or suppose this equation, let me just put this I1 equals to 1.5 ampere into this equation, I'll be left with 9 minus I2 equals to 2 into I1 plus, that means 1.5 plus I2. So when you are going to solve for this, you will see that your I2 will came out to be 2 ampere. Are you able to see this? Okay. So I1 has came out to be 1.5, I2 has came out to be 2 ampere. Now what we have to do is, we have to find out the current in this particular arm. You can see in this 2 ohm resistor, my total current is I1 plus I2. So the total current will be current in 2 ohm resistor that will be I1 plus I2, that means 1.5 plus 2, that is equals to 3.5 ampere. Okay, so now we have to check whether this is the option available in the question that has been given to us or not. So I can see that option number B has been provided as 3.5 ampere, and that must be the correct answer, because we have started with the correct approach and we have reached up to the correct answer. Alright, now this was the question number 1, which is having only one correct option, which is 3.5 ampere as answer. Now we will be moving towards the next question, that will be the question number 2. Okay. So, the question number 2 says that in the diagram, resistance between any two junction is R. We have been provided a figure before us, a circuit before us, and between any two junction, it has been given that the resistance is R. Equivalent resistance across terminals A and B is what? We have to find out the equivalent resistance across these two terminals. Now let me just again draw this figure. This is like this. P, A, this is B, and this is Q. What we have to do is, we have to find out the resistance, equivalent resistance across A and B. As you know that we have covered the finding methods of equivalent resistance in the lectures. I know you are pretty much intelligent that you will be yourself knowing that what we are going to do over here. In the question we have been given across any two junction. Let me just ask you one question. What do you mean by junction? What do you mean by junction? What is junction? If we are talking about junction, that will be a point where two or three resistance are being meeting. So in the question we have been given P and Q will be also a junction. So this is a junction because two resistance are meeting over here. This will also be a junction, this will be a junction, this will be a junction, this and this. These all are junctions. And among these, the resistance between any two junctions is R. So that means this is R, 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 R. This has been given. And we have to find out the resistance between A and B. What we are going to do is we are going to simplify the circuit first of all. How we are going to simplify the circuit? As you know that these two resistance, this and this, these two are connected in series because their one arm is here and the another arm is connected over some other point. So that means these two resistors are connected in series. So R plus R equals to 2R, right? Because in series we just have to add them up. So R plus R equals to 2R. Now this 2R resistance, let me just remove this because this has become a 2R resistance. So that will be like this. Now as you see that this 2R and R, they are connected in parallel because their one arm is connected at this point and their another arm is connected at this point. Suppose this is two resistors I am having in my hand. At one point their both arms should be meeting and at another point their another arm should be meeting. At that point we will be saying that these two resistors are connected in parallel. So that means these two arms at one point, these two arms at another point. So these two resistors are connected in parallel. So what is the formula of finding resistance between two parallel resistors? AB upon A plus B. So that means that will be 2R into R upon 2R plus R, or that will be 2R square by 3R equals to 2R by 3. So that means this resistance has now become as 2R by 3. This whole will be removed. Okay, let me just redraw this figure. In place of these wires, I am connecting resistors because we are talking about the resistors over here. Now this is point A, this is point B, this is point Q. This has become 2R by 3. This has been reduced now. Now again what you can see over here, this is R, R, R. How do we can simplify it more? Now again you can see this R and R are connected in series. Why? Because their one arm is here, one point is here and another arm is joined at two different points. So R plus R will be equals to 2R. Now again this 2R has been connected in parallel with this R. Again the total resistance will become 2R by 3. So we can now rub this out and we will be writing in place of R, as we have found out this 2R by 3, similarly this will also be 2R by 3. Right? Now the figure has been simplified more further. We have to find the resistance between A and B. This is point B. What more we can do? We can see that these two resistors are connected in series, 2R by 3 and 2R by 3. So that means it will become as 4R by 3. When you will be adding 2R by 3 plus 2R by 3, you will be left with 4R by 3. So that means you can further simplify this circuit as, okay, this is R, and this is R. This 2R by 3 has been solved as 4R by 3. So I can write this as one resistance, that is 4R by 3. Now you can see that this 4R by 3 and this R are now connected in parallel. And we know that to find out the resistance between any two parallel is AB upon A plus B. So A into B, 4R by 3 into R upon 4R by 3 plus R. So we will be having 4R square by 3 into 3 by 7R. So you will be left with 4R by 7, right? So that means this resistance we can write it as nothing but 4R by 7. Now as you can see again, these two resistors are connected in series. So that means 4R by 7 plus R. So that will be 4R by 7 plus R, or you can write it as 7 plus 11, 11R by 7. I can just remove this and I will be writing it like this. This is A and this is B. This is 11R by 7. Now as you can see, these two resistors are connected in parallel. So to finding out the equivalent resistance between A and B, the total resistance will now be, let me just remove it from here. The R net will be 11R by 7 into R divided by 11R by 7 plus R. So that means 11R square by 7 multiplied by 7 by 18R. So you are left with 11R by 18. This as the net equivalent resistance between any two points, that is A and B. So our answer has came out to be 11R by 18, and now we have to check in the options available 11R by 18. So I can see that option number D has been given as the similar option that we have found out.